All right, so last class we started acids and bases. We learned a bunch about acids and bases, some definitions, Arrhenius, Bronsted-Lowry. We learned about conjugate acid-base pairs, where we pair an acid and its conjugate base or a base and its conjugate acid. And we learned some strong acids and weak acids. There were some that you were supposed to memorize. So strong acids that are circled here or boxed in here, those are ones that you should know are strong acids. And some weak acids, two that you should know. And there was also this fun exception with sulfuric acid where the first proton, the first H that comes off, is strong, and then the second one is weak. And so we've got a single directional arrow indicating that this first one is strong, and the double direction arrows indicating that the second one is weak. So it doesn't ionize all the way. So in determining the hydronium H3O plus concentration for each of these solutions, we have to think about whether we have a strong or weak acid, because a strong acid will ionize completely, a weak acid will not ionize completely. We don't have the tools to figure out exact numbers for some of these. Like if it's a weak acid, we don't have the math tools available to us to do that. It's something that you can calculate, but that's something that you'll get to in 1B, assuming that you take the full Gen Chem series. Okay, so starting off with A, we've got 0.80 molar this thing. And this thing is an acid. We know that it's an acid because it's got an H in front. Is it a strong or weak acid? Who remembers? Who remembers if it's a strong or weak acid? It's a weak acid. That's acetic acid. This is the one that's in vinegar. Since it's a weak acid, it doesn't ionize completely. It will ionize a little bit. So it's going to have a concentration of H3O plus. What would be the maximum amount if it ionized completely that we could get? Does anyone know? How many H's could come off? What would be the concentration of those H's? Because H plus and H3O plus are the same. Ideas? If we have 0.80 moles per liter HC2H3O2, how many H pluses come off of each acetic acid, H2C2, H3O2? How many H's can come off? Can ionize? It's a number between 1 and 5.
3.
It's not 3? It's 1. We've got one hydrogen in front. That's our ionizable hydrogen. So we've got one ionizable hydrogen. So at most, we could get one H plus for every HC2, H3O2. We're looking at the maximum amount that we could possibly get out. So we could have, at maximum, 0.80 moles per liter H plus. We're not going to hit that maximum value because it's a weak acid. It's only going to partially ionize. So our concentration of H3O plus is going to be less than that amount. Do we have questions about that? All right, moving on to B, 2.25 molar HNO3, nitric acid. Is nitric acid a strong or weak acid?
Strong.
It is a strong acid. What does a strong acid do when it dissolves? How does it ionize? Completely or not completely? It ionizes completely, meaning that all of the hydrogens that can ionize will ionize. So all ionizable H plus will ionize. How many ionizable hydrogens does nitric acid have? 1. So we can get 1 H plus off. 1 H plus is going to be produced for every HNO3. So 2.25 molar HNO3 will turn into 2.25 molar H plus, or as it actually exists in solution, H3O plus. It's the same number. Who remembers what kind of acid HF is, hydrofluoric acid? Strong or weak? It's a very confident strong that somebody mouthed. It is a weak acid. Meaning that it will not ionize completely. So what is our concentration going to be? If it ionized completely, it would be this 0.70 molar since it's got 1 ionizable hydrogen. It's not a strong acid, so it's going to be less than that amount. So less than 0.70 molar. Questions about any of those? All right, moving on to bases. Our strong bases, just like strong acids, dissociate completely. So the strong part here meaning dissociates completely or completely dissociates in solution. And we've got a bunch of examples of strong bases here. What do all of these strong bases have in common? Hydroxide, they've got the OH. So that could be your signal that it's a strong base. This isn't going to work all the time, but all of these are ionic because the other part is a metal. And have hydroxide in them. So you might think to yourself, O, that's a strong base. O being OH, not just O. Another thing that makes them different, or something that makes them different from acids, is that they dissociate in one step. So in a single step, both of the hydroxides come off, unlike with sulfuric acid where we showed one proton comes off, then the next proton comes off. So for these, it all happens in one step. Sodium hydroxide is an example of a strong base. If you take sodium hydroxide and you put it into a solution, you're going to get sodium ions, you're going to get hydroxide ions. You're not going to have any sodium hydroxide units in solution. No sodium hydroxide intact in solution. It completely dissociates. Only ions exist in solution because it's a strong base. Weak bases are like weak acids in that they do not dissociate completely. The most common weak bases make hydroxide by accepting a proton from water. So for example, in this generic equation, B is just standing in for weak base. It's going to take one of these hydrogens from water. It forms the conjugate acid, and hydroxide is also formed in the process. So for example, for ammonia, ammonia picks up one of the hydrogens off of the water. It turns into its conjugate acid, ammonium, and hydroxide is formed. Hydroxide is generally what we are thinking about when we're thinking about bases. Is there hydroxide produced? There are a lot of weak bases. Organic amines, things that have nitrogen in them, are commonly weak bases. So like ammonia and pyridine, both of which are kind of stinky, are some notable organic amines. There's some notable weak bases. Another important weak base is sodium bicarbonate. Bicarbonate being another name for hydrogen carbonate. That would be an example of another weak base. Possibly a way that you could remember that baking soda is a weak base, or that it's a base. Baking soda reacts with vinegar, which has acid in it. It's an acid-base neutralization reaction. That's the classic science fair papier-mâché volcano sort of thing. Or lots of people's favorite cleaning hack that isn't actually a cleaning hack that I mentioned last class. So there's 3 examples of weak bases. For each of these, let's determine the hydroxide concentration for each of the solutions. So think about, is it a strong base or is it a weak base? And then how many base equivalents can it produce? How many hydroxides can it produce in solution? First thing we want to think about for A, calcium hydroxide. Is calcium hydroxide a strong or weak base?
Strong.
It is strong. Oh, that's a strong base. You might think to yourself. So this is a strong base. It's ionic. It's got hydroxide in it. So it's a strong base. That means that it completely or not completely ionizes. Completely ionizes. Completely dissociates. Just falls apart. When it falls apart, how does it fall apart? How many hydroxides does it make? It makes 2 hydroxides. So in one fell swoop, calcium 2 plus, and 2 hydroxides are formed. So we've got a little stoichiometry, a little ratio here, 2 hydroxides for every 1 calcium hydroxide. Or you could just see the little subscript 2 and say to yourself, there's 2 of them that we're going to be producing. Let's just multiply it by 2. Either way you want to work it, gets you the same answer. So 0.135 molar calcium hydroxide will turn into 0.270 molar hydroxide. What kind of base, strong or weak, is NH3? It's a weak base. How do we know it's a weak base? It's got a nitrogen in it. So it doesn't, or does not, completely ionize. If it were to completely ionize, what concentration of hydroxide could be made in the solution? What's the maximum amount of hydroxide we could make? It's the same number. Because it's going to pick up hydrogen from water. We saw this in a previous slide. Is this little thing. It picks up a hydrogen from water and turns the water then into hydroxide, and the ammonium is also formed. It's a 1-to-1. All of our weak bases that we learn in this class are just going to produce one base equivalent. So the max, if it was strong, would be a 1-to-1 ratio. So it would be 0.95 molar hydroxide. It is not strong, right? So it's going to be less than that. So our concentration of hydroxide is less than 0.95 molar. For those of you that have trouble remembering which side is bigger, the alligator eats the bigger number, right? So the 0.95 molar is bigger than the concentration of hydroxide. Hydroxide concentration is less than 0.95 molar. For our last example for bases, what kind of base is KOH? It's strong. It's got a hydroxide. Oh, that's a strong base. So this is also going to completely ionize. How many hydroxides will it form when it dissolves in water and ionizes? 1. So it's going to be a 1 hydroxide produced for every 1 potassium hydroxide put in. So our concentration of hydroxide is 0.50 molar. Questions about those? Again, the weak bases to know: NH3, C5H5N, ammonia and pyridine respectively, and then stuff like baking soda, sodium bicarbonate, NaHCO3. Water, we mentioned earlier, is amphoteric, so it can do an acid, it can also do a base, it can give a proton, it can also take a proton. It's a little bit like the penny dish at the grocery store. Take a penny, leave a penny. Or maybe that's more like a cafe or a diner. Anyway, it does both. And even in pure water, it's just water, there's nothing else in there, it's also going to do this. And we call this self-ionization because it's water doing an ionization action with also water. So one of these is giving up H to the other one. And so we make a little bit of acid and we make a little bit of base. Notice that we've got the double-sided arrows here, so that means this is not happening completely. There's mostly water there, but there's also a little bit of ions that are formed. It's a continual process. The self-ionization occurs to a very small extent, and we actually know what that extent is, how much it does that. It also produces equal amounts of H3O plus and hydroxide. So if it's just water, our concentrations of H3O plus and hydroxide are the same. And in pure water at 25 degrees Celsius, that's always what it's going to be in this class, that amount is 1 times 10 to the minus 7 molar. So like a 10 millionth-ish of a molar. Very small amount. We have a new constant that we're learning, the ion product constant. This constant for water, K for constant, W for water, is the ions multiplied by each other. So H3O plus, that's one of the ions. Hydroxide is the other ion. If you multiply 1 times 10 to the minus 7 by itself, you're adding up the exponent, so it's 1 times 10 to the minus 14. This is important. And also, I'm pretty sure I'm going to give it to you because one less thing to memorize. There's enough concepts to know. Questions about any of that? So this Kw equals the concentrations times each other. We're going to take use of that, make use of that in our upcoming slides. If we're in a neutral solution, our concentration of acid is equal to our concentration of base. H3O plus is what's produced by acids. Hydroxide OH minus is what's produced by bases, either directly or indirectly. To summarize and to add a little bit more information, in a neutral solution, acid and base are equal. In an acidic solution, we have more acid than base. There is still going to be some base present. In a basic solution, I'll write acid less than base. So acidic describes something where we've got extra acid, more acid than base. Basic describes something where we've got more base than acid. And in all aqueous solutions at 25 degrees Celsius, which will be true in this class, this bottom bit, which I boxed in earlier and wrote is important, is also true. The concentration of the H plus times the concentration of the OH minus is equal to our Kw, which is 1 times 10 to the minus 14. These two numbers, those two quantities, H3O plus and OH minus, are related. Oftentimes when we're talking about acid and base, people get confused because we're dealing with negative exponents. So I've written out the decimal form of those negative exponents as well. So we're looking at an acidic solution. It's got a hydroxide concentration of 1 times 10 to the minus 4 molar and a base concentration of 1 times 10 to the minus 10. Since these are negative exponents, the smaller negative exponent is actually the bigger number. And that's part of why I wrote out the decimal form. Right, we can see that the acid part is much bigger than the base part. We got more zeros in front of our base part. Since we've got more acid than base, that makes it an acidic solution. In this case, we've got like 1,000,000 times more acid than base. It's not even close. And then for our basic solution down below, if it's got an H3O plus concentration of 10 to the minus 9, 10 to the minus 9 is this number that follows it. It's going to also have a hydroxide concentration of 10 to the minus 5. That's the number that follows it. So our base number here is bigger than our acid number. They're both very small. But again, the smaller negative exponent is the bigger number. And it's basic because it has more base hydroxide than acid, hydronium. Do you have questions about exponents? Why one of those numbers is bigger than the other? These are just made-up solutions. All right, we can use Kw in calculations. Indeed, we're going to use Kw in calculations. Kw is our water ionization product constant. It's the concentration of H3O plus times the concentration of OH minus, so acid concentration times base concentration, and it's got a value of 1 times 10 to the minus 14. So we're going to do some calculations with this. This is basically a formula. Right, we've got one variable times another variable equals this constant. So in each of these examples, we're provided with the hydroxide, and we can calculate the H3O plus concentration. So I'll show you how to do that. So starting with H3O plus times OH minus equals 1 times 10 to the minus 14. We have hydroxide, and we want to find hydronium, H3O plus. So we want H3O plus by itself. To do that, divide both sides by the hydroxide concentration. And what we'll be left with is H3O plus concentration equals 1.0 times 10 to the minus 14 divided by the hydroxide concentration. So for our first one, H3O plus concentration equals 1.0 times 10 to the minus 14 over the number that we were given, 1.5 times 10 to the minus 2. there's a decent amount of opportunity here to accidentally put in the numbers incorrectly. I would recommend parentheses. You don't necessarily need it for the number on top, but it doesn't hurt. So the numbers, all the numbers on top together in one bunch of parentheses. So those numbers are all together. And then the numbers on the bottom all in one bunch of parentheses. Please take a moment and plug this into your calculator to make sure that you are getting the correct answer. Because if you don't know how to do it on the exam, I'm not going to help you, because it's an exam. So if you get the wrong thing now, then we can troubleshoot, hey, why'd you get the wrong number? So the number that you should have gotten, 6.7 or 6.6 repeating until it's a 7 times 10 to the minus 13. And our units would be molar. So if you got something that was not that was like significantly different from that, it's possible that you didn't put parentheses around your number on the bottom, or something else happened. Any questions so far? Okay. And then the other question that we're trying to answer is this solution acidic, basic, or neutral? AKA, do we have more acid, do we have more base, or do we have equal amounts of acid and base? We've got our hydroxide concentration here, our H3O plus concentration here. Which of these two numbers is bigger, 1.5 times 10 to the minus 2, or 6.7 times 10 to the minus 13? Which one's bigger? The 10 to the minus 2 one is bigger. So that's the bigger number by a long shot. Since that's the bigger number and that's our base, this is a basic solution. Basic solution meaning more base than acid. For our second and third ones, we're using the same exact formula. So we're using this formula over here on the right. Concentration of H3O plus is our Kw divided by our hydroxide concentration. This is also one where if you remember some facts, you don't actually have to put it in your calculator. Our H3O plus concentration is the same number. You will get the same answer if you put it into your calculator, assuming you put it in correctly. If you put it in wrong, then you'll get 1 times 10 to the minus 21, or something like that. Is this second solution, is there an excess, or is there more acid? Is there more base, or are they the same? They're the same. So this is a neutral solution. We've got the same amount of acid and base. So it's not acidic, it's not basic, it's neutral. And then for the last one, we're putting in 1.0 times 10 to the minus 14 I'm going to write what I put in my calculator, or what you could put in your calculator to get this answer. So that's one thing that you could put into your calculator. Another thing that will get you the exact same number, but doesn't require you putting in parentheses, is that. So this is utilizing the dolphin key, the dolphin noise key, which looks like this on most calculators. It's two capital E's next to each other, famously the sound that dolphins make. And if you press that button, it'll give you a small capital E, the diminutive capital E, and that stands in for times 10 to the whatever follows it. So you can also do that. If that's confusing to you, forget it. I didn't say anything about it. Just, it doesn't exist. Or you can do it this way. So 1 times 10 to the minus 14 divided by 8.2 times 10 to the minus 10. Zero 0.00001 molar, aka 1.2 times 10 to the minus 5 molar. And that's our concentration of hydronium, which is acid. Then to figure out if it's acidic or basic, we compare. Is our acid number or our base number bigger? The acid number is bigger. Since we have more acid than base, this is an acidic solution. Questions? One way to check that you've done these problems probably correctly is if you look at the exponents. For our last example, we had 10 to the minus 5, and we were given 10 to the minus 10. If you add the exponents up, it gives you minus 15. That's plus or minus the 10 to the minus 14. That's good, that's what we want. You should always be, if you add those exponents up, they should be plus or minus 1 of this 10 to the minus 14. If you get 10 to the minus 21, if you get 10 to the minus 15, sorry, not 15, 16, if you get 12 for your exponents when you add them up, that's a sign that something went wrong. If that doesn't make any sense to you, forget about it. I never mentioned it. But if it helps, great. Congratulations, there's a new tool for you. We're going to build on that. So as fun as scientific notation is, and negative exponents are, there's a nicer way to deal with acidity and basicity, the amount of acid and base that we have. And that's the pH scale and the pOH scale. So pH, you may know, is a measure of acidity. We've got a table or a chart from our book online of a bunch of pH values. If your pH is less than 7, that's an acidic solution. If it's above 7, that's a basic solution. If it's right at 7, that's a neutral solution. This works for 25 degrees Celsius, which is always what it's going to be for our class. So if we're right at 7, pure water is right at about 7. Going more towards the acidic side, hydrochloric acid is very strongly acidic. So that's in the low pH section, in the 1, pH 1, pH 0. You can get into negative pH values. And more towards the basic side, we've got things like sodium hydroxide and bleach. And Drano would also be up in that very basic side. You can also see lemon juice down here on the acidic side. let me box this in. You should know pH less than 7 is an acidic solution. pH greater than 7 is a basic solution. Another name for basic is alkaline. So some fancy waters will tell you that they're like alkaline volcano water from Hawaii, and it's like a pH of 8.8 or something silly. I mean, it tastes a little soapy, feels weird in your mouth, and it costs $3 a bottle. Alkaline water is slightly basic. I wouldn't waste your money on it. To find pH, it's a whole block of text here, partly so that you can reference it without me talking you through it, and hopefully it all makes sense still. We're going to start at the top. So our baseline, our big important equation, little p, capital H, is negative log of H3O plus. So the little p, I forget what it stands for, but it means negative log. And log is a key on your calculator. You might have to press it twice depending on what calculator you have. So ln is not the same as log. ln is a specific form of log. So if you've got the ln log key, if this is on your calculator, press 2 times to get log. Some of you might not have that. My calculator has that. If you press it once, it'll give you ln. If you use ln instead of log, you will get the wrong answer 100% of the time. We're going to talk a little bit about logarithms, which is always fun. You don't need to know how logarithms work, so you can enjoy that. But we're still going to talk about them. So a logarithm has the form log b is going to be some base. The b is usually 10 unless you specify otherwise. For ln, that log is a natural number called e. I think it's e. The log of some number gives an exponent. And logarithms are confusing. They just are. A logarithm can also be rewritten as the base raised to the exponent equals some number n. So this is like asking a question. The base raised to what number equals the number that we put in this log? That's all that a logarithm is trying to find out. Your calculator does it for you. You don't have to do any of that. The reason that we have logarithms, the reason that we use logarithms, is because it's an easy way to express really large numbers in a compact form, and we use them to get to space. So as a question, base raised to what exponent gives the number n? So looking at 2 examples, we've got 100. 100 is the same as 10 to the second power. So if you put in log of 100 to your calculator, you'll get 2. It's just giving you this exponent out. If you do 1,000, 1,000 is 10 raised to the third power, or 10 cubed. So if you put that in log 1,000, it gives you this exponent out. The reason that I used things that are nice round numbers with 10 is because otherwise they get really weird and hairy. So we're doing the simplest possible version. And just a reminder for you, in case you look back at the slides later, you do need to know how to put logarithms into your calculator. You do not need to know how they work. If you can put them in correctly, if you can undo them correctly, it's good enough. Questions about logs? Good, I love it when there's no questions about logs. We're going to use that equation that we saw earlier. pH equals negative log H3O plus. We could also put just H plus in there. we're going to use that equation to find the pH of these solutions and also indicate whether it's acidic or basic or neutral. So give that a shot. Another note, this negative, you probably have a negative key. It's different than your subtract key. On my calculator, it's a minus inside of parentheses. If you use the subtract, it'll give you syntax error. And syntax error is not the right answer for this question. All right, so plugging this into our calculator, negative log 5.8 times 10 to the minus 4. This is another place where you can use that little e key, little capital E key. Has to be the capital E, the lowercase e is a different thing. You get a value of 3.2. Hopefully you got that. A check is something that you write out, usually your name and amount, who it's to, like giving money to somebody. A check, in this case, relevant to our example, to make sure that we got the right answer, our exponent was minus 4. Our value that we got out was 3.2. That's plus or minus 1 of the negative of our exponent. These should always be about the same number, plus or minus 1 or the same number. So if we got 7 or 12 for some reason for our answer here, that is not plus or minus 4, so we would know that it's wrong. So these should be plus or minus 1 from each other because of the way exponents work. All right, so our pH is 3.2. Is that an acidic, basic, or neutral solution? It is acidic. Neutral is 7. Basic is above 7. And acidic is below 7. Question?
What acid would have an acidity of 3.2?
I don't know off the top of my head what would be a 3.2. I'm guessing lemon juice would be kind of in that ballpark. That might be a little bit on the low acidity side for lemon juice. I think lemon juice is 2 to 3. Or you could just have a dilute solution of hydrochloric acid or some other strong acid. What if our H3O plus concentration is 1 times 10 to the minus 7? This is going to give us a pH of 7. If we have a pH of 7, does that mean it's acidic, basic, or neutral? It is neutral. Questions about pH? We can also work backwards. So logarithms can be undone by doing what's called an anti-log. Basically, the way that an anti-log works is make each side the exponent for 10, which is the base of our log. So pH is negative log H3O plus. We can turn that into this equation down here. So first, we would multiply both sides by negative 1 to get to that. And then we would raise both sides as the exponent of 10, which is called an antilog. So this is the important equation, and just showing you very briefly the quickest possible how to get to that. So 10 raised to the negative pH will give you out your concentration of H3O plus. So this is working backwards if we start from pH and want to get our concentration, rather than starting from concentration and working to our pH. This is another, you don't need to know how we got it, you just need to know how to put it in your calculator, when to use it. Okay, so let's say that we've got one of those fancy alkaline drinking waters from Whole Foods maybe. We want to calculate our H3O plus concentration. 10 to the negative pH is the concentration of H3O plus. So 10 raised to the negative 8.87 This might also be a thing that you need to press a button twice. And my calculator gives me the mostly unhelpful this number. It's not entirely unhelpful because it's like, yes, that is sort of true, but also it's missing some information. Because this is actually 1.3489 ... times 10 to the minus 9. So the button that I use to get that, there's E with a box, and then 10 with a box. If you press that button 2 times, you get the 10 with the box, and then you just put the number that you want in the box. To get this 1.3489, et cetera, times 10 to the minus 9, you can put your calculator in scientific notation mode. So you'd press the mode button, at least on my calculator, that's what you do, and then select SCI. It's the second line. Your calculator may be different, but that'll put it in scientific notation. Then all numbers get put into scientific notation, and you can plug that in again. I'm sure there's another way to do it, but that's the way it works on my calculator. That's how I do it. Non-calculator questions about doing that problem? Another thing that you could do is just multiply this number by like 1,000 or something, and then it'll basically scooch some of those zeros out of there, and it'll give you more decimal places. So that would be another way to get more numbers instead of just a 1, because that's not very helpful. So there's not only a pH scale, there's also a pOH scale. The important part that you need to know, or an important part I suppose that you need to know, would be this pOH equals negative log OH. So again, P in this context means negative log of whatever follows it. So OH for hydroxide. It's the same exact thing as pH with H3O plus. We've just switched the H, turned into an OH instead. If I remember correctly, I give you all of these equations on the exam, but you need to know which one to use and when. There is a cool property of logarithms that you're not going to enjoy probably because it's not a math class, you're probably not math majors. But we can construct a relationship between pH and pOH using this product of logarithms, the product's law. and our Kw. So let's start with our Kw. You don't need to know how to do this. I'm just showing you because I think it's cool. And some of you might think to yourself, oh, that's interesting. And that's good enough reason for me to do it. What we can do to this whole thing is negative log both sides. So we get negative log Kw equals negative log H3O plus times concentration of hydroxide. And thanks to our friend the product's law, things that are multiplied inside of a logarithm can be separated out to their own logarithms. So we're going to use that property. So we're keeping the negative log Kw on the left side, but splitting the things that are inside. So we get negative log concentration of H3O plus. And it would be plus, but we've got a negative. So plus negative, which is the same as just negative, minus log OH minus. I'm going to actually leave a plus in here because it is helpful. We know of some things that are equal to negative log of H3O plus. We know something that's equal to that. We know something that's equal to negative log of the hydroxide. Right, they're pH and POH. Again, you don't need to know how to do this. I'm just showing you so that you know where it came from. If you don't find it helpful, forget about it. We never talked about it. It didn't exist. It doesn't exist. So we can plug in from each of these. Right, so we can plug in pH for negative log H3O plus. We can plug in POH for negative log OH minus, and we'll still have this plus left over. So pH plus POH. And helpful for the left side is that Kw is equal to 1 times 10 to the minus 14. If you evaluate negative log of Kw, meaning that you plug it into your calculator and you get a number out, this is just 14. So 14 equals pH plus POH. Wow, what a cool relationship. That's an easy equation. Again, don't need to know how to get it. We're going to be using it though, so you do need to know how to use it. So pH plus POH equals 14. And this lets us quickly and easily move between pH and POH, which we're not doing on this slide, but we will be doing at some point. POH equals negative log hydroxide. So we're going to plug in negative log 2.75 times 10 to the minus 8. We would expect the number that we get out to be 8 plus or minus 1. And the number that we get out is 7.56 for our POH. We can work in the opposite direction. It looks eerily similar to what we did with pH and H3O plus concentration. So for pH, it was 10 to the negative pH equals the concentration of H plus. we can put in instead POH and OH minus. And it's the same thing because it's the same relationship. So 10 to the negative POH equals concentration of OH minus. So plug in 10 to the minus 3.54. We should get a number with an exponent that's plus or minus 3. Or negative 3, rather. So 10 to the minus 3.54, 2.88 times 10 to the minus 4. Questions, confusions, contusions? Collusions? Okay, and then the last thing, because I guess we're not doing that, we're not utilizing this fun rule, this fun thing that we've got here. I guess because I just forgot to put something in. The last thing that we're going to talk about is arguably the most confusing. We save the best for last. Buffers. A buffer contains significant amounts of a weak acid and its conjugate base. It has to be a weak acid, and it has to also have its conjugate base. We could also have a weak base and its conjugate acid. Buffers are very important for us. Our body has built-in buffers. As it turns out, if you raise or lower your blood pH just a little bit, a healthy blood pH is 7.36 to 7.40. That's a very small range. If your pH dropped below 7 or you got it above 7.8 somehow, that's it. You're done. No more living for you. And to help us keep a healthy blood pH, we've got a complex series of buffers in our bodies that our body automatically manages and takes care of. Let's look at one possible buffer system. One possible buffer system would be acetic acid. Acetic acid is a weak acid. Sodium acetate is this, NaC2H3O2, affectionately referred to by me as nacho. So this is an acetic acid nacho buffer system. So HC2H3O2 and the version without the hydrogen in front. So the only thing that's different between these two has H and no H. They differ by one H plus. We've got a sodium standing in for the H instead. This, I think, is the part that often confuses students. They're like, oh, it's got something else in the front. It must not be the conjugate base. In order for this to exist in like a form that we can handle, that's like a solid, it has to be neutrally charged. And so that's why we've got the sodium. It gets removed if we dissolve it into solution, and then we would have the C2H3O2 minus that we'd be looking for. So in solution, that would look like this. And this is probably what you would be looking for, the C2H3O2 minus. That's what you would be looking for as the conjugate base for acetic acid. So if we have both of these things together in a solution, significant amounts, if we add a base, our acetic acid has a proton that it can get rid of to neutralize the base. So that neutralizes the hydroxide. At the same time, in this solution, we've got our acetate. That's from the nacho, right, the C2H3O2. So if we've got extra protons, like we add some acid into our solution, it can pick that up and neutralize it in the process. And it just reforms the acetic acid. So if we add acid, if we add base, both of those can be neutralized. And that's what happens in a buffer solution. So in this diagram, we've got Han and An. An is just anion. And HAN is the weak acid. So we can add hydroxide from a strong base, and that's going to pull off some of these H's and form water. So we've neutralized the hydroxide. On the other side, we could add H+, for example, from a strong acid, and we've got some extra HANs that form in solution. Those formed when we neutralized the acid. There'd be some other ions that would be floating around. So just showing you that we can do both of those. Which of the following is a buffer solution? So as a reminder, for a buffer solution, we need weak. It has to be weak, it cannot be strong. Acid or base. And conjugate, base, or acid. Our conjugate and our non-conjugate, the difference is a proton. One of them has it, that's the acid. One of them doesn't, that's the base. So take a second, look through each of these, and figure out which of them, if any of them, maybe multiple of them, is a buffer solution. To start, let's classify as many of these as we can as acids or bases. So starting with HCHO2, is that an acid or a base? It is an acid. Any guesses about whether it's a strong or weak acid? It looks kind of like a different acid that we know is a weak acid. This is a weak acid. It looks like acetic acid. acetic acid, it's HC2H3O2, which is one of the ones that we need to memorize for weak acids. We've got a nacho here. If this dissolved in solution, which it is, it's aqueous, what would we have? What would one of our ions be? Sodium and CHO2 minus. So we've got one of our points that we need. We've got a weak acid. Do we have in here the conjugate base? Something that's different by only an H. Yes. This CHO2 minus, this is HCHO2 without the H in front. Right? It gets released as an H plus. So we've got weak acid and conjugate base. This is a buffer solution. Okay, moving on to B. HCl is what? An acid, a base, neither? It's an acid. What kind of acid is it? It is a strong acid. Since it's a strong acid and not a weak acid, this is not a buffer. You cannot form a buffer with a strong acid. Has to be a weak acid. All right, looking at C, CH3NH2, any guesses about whether that's an acid or a base? Do we have an H in front? No H in front, so it's not an acid. We have an N. This is an organic amine, meaning it's a weak base. Not one that you're expected to know, but we can identify that it's got an N in it. That makes it a weak base. If this were to pick up an H plus, what might it look like? We'd have one extra H somewhere in there. So it might, for example, look like CH3NH3. Plus. The Cl is on here because we've got a molecular formula. So the Cl minus, we've got an ionic compound in there. So we've got a weak base and the conjugate acid, also a buffer. We're almost done. So that one is also a buffer. In D, is NH3 an acid or a base? It's a base. What kind of base? It's a weak base. To have a buffer, we need also its conjugate. So for a weak base, that would be a conjugate acid. What is sodium hydroxide, NaOH? That's also a base. So this is not a buffer. Additionally, to add insult to injury, it's even a strong base. So, not a buffer. Questions? I typically put one buffer question, maybe two. Maximum of 2 buffer questions. On your exam, it'll mostly just be identify which one's a buffer.